Well, hello, friends. Welcome back to Commute Talk. It's covered in snow here today, which is pretty nice. A little more Christmas for me. And today I thought I would talk about stacks and operating system implementations of the stack, actually. Because something that a lot of people don't realize about the stack is that it is lazily allocated. And the way that it works in many systems is that when you start a new program, the operating system will allocate some amount of virtual address space for the program stack. In Serenity, we allocate 4 megabytes up front, and on something like Linux, it's configurable. You can set it with like ulimit-s, I think. And that doesn't mean that we're taking up 4 megabytes of physical memory. It just means that we allocate that much address space for the stack. And then what we do is that we fill in that address space with physical RAM on demand. So when you first start a program, then the stack pointer is at the very end of that address space, or at the very top of the stack, if you will. And then when you push things on the stack, you are moving that stack pointer further down the address space of the stack. And of course, the kernel will put some stuff on the stack for the new program, like the arguments vector and the environment and like auxiliary variables and stuff like that. But so there'll already be a little bit of that happening immediately on program startup that you don't generally control because it happens before main. But after that point, it's all up to you how you use the stack. And something that a lot of people don't realize about this is that when you put things on the stack, you are growing it, and the stack never shrinks again. And this is because when we grow the stack on demand, we just do that using the page fault mechanism of the CPU. And how that works is that when you allocate a piece of virtual address space, then you're basically telling the CPU, hey, these addresses here, this address range is valid, but if somebody tries to use it, let me know so that I can actually put some physical memory there. And then there's this notification mechanism in the memory management unit that's called a page fault that informs the kernel that, hey, this user space program is trying to use this memory. You said I should notify you. Here we are. And then the kernel has to go and allocate physical memory and put that in there and then resume the program. And the program is none the wiser. It's just storing stuff on the stack. But what happened behind the scenes is that now a piece of physical memory was allocated and put into that slot for the stack. And it's basically not reasonably possible, as far as I know, to reclaim that memory at any point, because after all, it's just valid memory, really. Like, just because you if you go deep into a call stack, for example, like you'd call something recursively, and at every step of the recursion you allocate some amount of stack memory. Say that you have a character buffer on the stack in your function that calls itself. That will quite rapidly grow because each stack frame allocates that buffer. And even though it's not something that typically happens, and you probably don't want to do this, that memory does remain valid after you exit the function at the various nesting levels, because the stack is just part of your program address space. So the kernel does not reasonably know if it can ever reclaim this memory. I guess that's what I'm trying to say. So it just doesn't do it. And I know that Linux they used to have this thing in their page fault handler where they would look at the faulting address and check, hey, is this below the stack pointer by a certain like fudge factor or fudge margin? And if so, they would say, hey, this is like an erroneous access, right? Because you should never access memory that far below your stack pointer. But they actually had to remove that because it was breaking compatibility with some programs. I don't recall exactly when that was. It was some time ago that they realized that it was breaking stuff. So Otherwise, that's kind of a nice thing, right? Like, you could potentially catch some bad behavior that way. But anyway, so I think many people believe that if they just allocate something on the stack, then it's basically zero cost, because you learn how it works and you see that, okay, it's just moving the stack pointer, and then at the end of the scope it just moves the stack pointer back, and there were no calls to malloc and free, and your program's heap did not change. But because of the lazy page allocation mechanism that most systems use, in practice, this ends up committing a lot of physical RAM to your program that can never be recovered. At least not in any way that I can think of, but maybe there is a way, and if so, I would love to know about it. I suppose if you could sort of, if you could make the ABI stricter, and you could say that, like, oh, it's never ever valid to access memory below the stack pointer after you have moved the stack pointer or something like that. But as far as I know, there are no requirements like that anywhere. So it's something that you kind of have to support. And then, of course, it's also possible for a user space program to allocate his own stack, because the stack pointer register is not privileged. So user space programs are able to retarget their stack pointer wherever they like. So, for example, you can mmap a piece of memory and then point your stack pointer to it, and now that's your stack. So the kernel would be kind of at a loss when to reclaim memory from something like that, because how would you know? Anyway, it's kind of an interesting problem, actually, because I guess if you could combine it with, if you would have something that makes sure that you zero out all the memory, like the compiler would emit code that zeroes out all the memory when exiting a scope, all the stack memory, and then you could combine that with some kind of mechanism in your kernel that finds completely zeroed out pages and then sort of coalesces them into the shared zero page. Then you could sort of like incrementally recover that memory by sharing it instead of having unique copies. But that's like a whole thing, right? And I'm not aware of any such compiler option that would say like zero out the stack after leaving it behind. Wow, somebody drove into a ditch here. Poor guy. Anyway, yeah, so that's what I wanted to say about stack memory today. So be aware that when you're using it, you may not be recovering as much memory as you think you are. So it's good to look at the stack in your memory map output in your operating system of choice and see how much of it is actually dirty and resident, because that's something that's definitely bitten me in the past. Like I would put like a character buffer of 64 kilobytes on the stack and think nothing of it, and then call that function in various places that were already pretty deep in the call tree or in the call stack, and then I would end up with something like 1 megabyte of stack, and with no way to recover it. Just something to think about in case you didn't know about it. I don't know, I just felt like talking about this today, so that's what we did. And I'm out of things to say about this topic, so yeah. Thanks for hanging out with me on the commute, and I will see you guys next time. Have a great Friday, okay? Okay? Bye.